Welcome everybody. You may see that we have a camera here. So this is a new initiative we're starting as a collaboration between Monash and ANITA, the Australian National Institute for Theoretical Astrophysics. So the goal is to record some of the theory-themed astrophysics talks and then put them on the ANITA YouTube channel so that people at institutions who don't have the luxury of having regular speakers can still benefit and enjoy the wisdom of some of our visitors. But today, as sort of the inaugural one of these ANITA recorded astro seminars, we have the pleasure of hosting Hagai Perets from Technion University in Israel. I've known Hagai for quite a number of years, and so I was trying to remember actually on the way over here the first time that I met Hagai. And the first time I think was at a seminar he gave at Northwestern more than a decade ago. And Hagai started his seminar with reminding everybody that he comes from a family of storytellers, and he told us a beautiful story at the start of the seminar. And then I sort of remember being a little bit almost, it was so wonderful, I remember being a little bit almost disappointed when at some of the subsequent talks I heard Hagai give, there was no preface of a story. But then I realized, actually, that's not necessary with Hagai because the subject of the talk is itself a beautiful story. And so, therefore, without further ado, over to Hagai Perets.
So, thank you very much. I'm really enjoying the visit here. And of course, Ilya just promised you a story. And yes, my dad is a storyteller, so I like to tell stories. And I'd like to tell you the story of supernovae. And it's in many ways, it's a story of paradigms lost and regained in some sense. In any case, before I begin, just to mention that most of the work here is actually done by my outstanding student, Yosef Zinati, also work with collaboration with several other people who contributed to various parts of these things. So, but of course, I need to begin with a story. So I'm going to tell you a story. So the question is, what is a good story? Well, my dad tells me that a good story always the really best ones have all of these four components: religion, royalty, sex, and mystery. Okay? And I can actually give you a very short example for that. So just think about the following story. Oh my God! What is that? Well, religion. I just mentioned religion, God, right? Okay. Said the princess. Royalty. Okay. I'm pregnant. Sex. But I don't know from whom. Mystery. Okay? So my story today would not really have all of these, but religion, well, we have science in the church, and that's always interesting to think about the things that happen, and Supernova went through this avenue a bit. Royalty, well, we don't really have royalty, but scientific equivalent, we do have Nobel laureates. Sex, well, not exactly, but when two white dwarfs come intimately close, there's a lot of fireworks, let's just say, okay? And mystery, well, that's what science is all about. So let me tell you a story of the origins of thermonuclear supernovae. And you can think about the stories starting even thousands of years ago. Think yourself of living at a time, not so many light pollution. You go outside, look at the stars. Actually, in Australia, in many places, we can see them very nicely. And people at the time could say, I know the passes of the sky like the passes of my own hometown. People really knew the sky. And they intimately knew the stars. So when they saw a new star coming out in the sky, which was not there before, it was a surprise. It was something new. Okay? And the story of supernova really begins with this observation of things that look like new stars in the sky, or nova, from the basically new, something new in the sky. And maybe I think the formal, or at least the written documents about supernova starts all the way from more than about 2,000 years ago, plus minus. And these are records of supernova events, or these new things in the sky, starting from the Chinese and maybe some of the Roman literature. And we can call them supernova 185 when they actually been seen, in a sense. And we have many of those seen in our galaxy by past observers. I mentioned here confirmed and unconfirmed, and I'll explain a bit in a second what I mean by that. So, in a sense, already the discovery of supernova already broke a paradigm. Think about the Aristotelian paradigm of the immutable heavens. So people thought we have the Earth, the Moon, then we have Mercury, Venus, the Sun, etc. You have all of these kind of circles in the sky, and with all of the planets. And the outermost one was the immutable heavens, just the stars that stay there. And in a sense, seeing new stars coming in the skies already broke this paradigm of nothing really changes in the heavens. So that was interesting. Supernova already very early started to break some of the basic paradigms. And since many of you are not necessarily familiar, or at least closely familiar with type 1a supernova or thermonuclear supernova, I'll go slow and then get faster and faster as I advance. I hope to take at least most of you all the way through the lecture. But feel free to stop me and ask questions at any level. So at this point, we have a very simple classification of supernovae, or actually just novae. OK. Later on, people realize there are actually even more, let's say, energetic events, and they call it supernova, and we'll get to that. So, of course, we have all supernova remnants that many people have seen. These are actually not real colors, you probably know. These are mostly in X-ray. And you can see all of these supernova remnants, which are basically places in the sky where people saw supernova in the past. You can see the years. And when you look today with current observational capabilities, we can actually see these supernova remnants. Basically, the remnants of the explosion that are still expanding in space at very high velocity of hundreds of kilometers per second. And you can see the gas material coming from the explosion starting at those times and still expanding to this day. And many of those observed supernova I can see today the supernova elements, and they are confirmed. But some others are not actually confirmed because people don't see them today, either because we didn't correctly understand what was the location people discussed in the past, or maybe they weren't really actually supernovae, but something else, some kind of other variable stuff on the sky. So continue and jump over to the modern era. And if you think about the first supernova in the modern era is 1885A, or S Andromeda. This actually took a very important role in playing in the cosmological debate of Curtis and Shapley. You might know whether they were wondering whether we are living in an island universe, the galaxy is the whole universe, or other let's say universes, or in a sense other galaxies. And one of the arguments was that people saw in the sky that there was like these small smudges in space, like M31. And people did not know what they are. Are there other galaxies, or are they just some kind of clouds? And at some point, 1885, they saw a kind of a transient supernova, something light coming from it at very high energy. And the debate was whether this is another galaxy, and the supernova is in another galaxy, or is it explosion in our own galaxy, and this is not another galaxy, but in our own galaxy. And the difference, of course, is that if it's in another galaxy, it's much, much further away than in our own galaxy, which means the energetics of it are far, far higher. Okay? And people say, this is impossible. Such an energetic explosion is unlikely. And this is why the argument was that it has to be galactic, and these smudges are not other island universes, but are actually part of our own galaxy. They were wrong in that sense, but this debate actually comes back again and again each time we have a new types of transients. For example, gamma ray bursts, GRBs, people were debated whether they are galactic, extragalactic. Same arguments, if it's extragalactic, it should be extremely energetic, and so people thought it may be just galactic. We have with FRBs, we had the same kind of issues. So these kind of things coming back again and again. But already you can see how this discovery play a big role in the evolution. So if we can continue, we go to the 1920s and the supernova hunters. So Zwicky, Baden, Minkowski are some of the big names that started looking systematically on the sky and tried to look for surveys of transient events, things that change in the sky. And they started discovering all of these supernovae. This point people already know that these are real galaxies, other galaxies. And they saw supernovae not in our own galaxy, but in other galaxies at very large distances. And actually, to this date, Zwicky, I think, is the single most highest discovery of supernovae. He discovered 120 supernovae. Today, of course, we find many more in surveys, but as a single observer, I think he's still the record holder to this day. In a way, he called these supernovae because these are not just a novae, these new stars in the galaxy. These are now understood very energetic explosion because you can see them to very large distances from other galaxies. people started using the tools of the trade, started looking on the spectra. You see this light in the sky. What spectra do we see? And realized there are actually two types of these kind of events. And they call them type 1, where no hydrogen is seen in the spectra, and type 2, where we do see hydrogen lines. Interestingly, but they also started looking on what we call today the host galaxy distribution that people actually use to this day. Started looking on what's the distribution of the host galaxies of these events. Some of these supernovae are observed in so-called elliptical galaxies, some of them in spiral galaxies, and he realized that one type of those, type 2, were observed only in kind of spiral galaxies, while type 1 supernovae were observed in both elliptical and spiral galaxies. It wasn't understood why was that the case. So now we have two types of supernova, type 1, type 2, okay? A bit more complicated, but still a bit simple. So if you can continue, so Zwicky already very early on, basically a year after the neutron was discovered, the particle, he suggested he could actually have a whole star made of neutrons, and that was suggested as part of the idea of how you have this supernova explosion. Basically, he suggested a very massive star at some point collapses, and the protons and electrons coming together and form neutrons, and you get a kind of a very compact neutron star, and everything basically goes onto that, get bounced, and goes back again as an explosion. A very simplified model. It didn't actually go into the details, but later models that I discussed actually did go to this, through the details of this stuff. And we'll do a bit of sidetracking here, just a bit of history. So the first neutron star that was actually, as already suggested, predicted by Zwicky very early on, was only discovered by, at about 1967 by Jocelyn Bell. And our advisor, Anthony Hewish. And as you probably know, a few years later, Anthony Hewish, her supervisor, received the Nobel Prize, while Jocelyn Bell, who actually discovered that, also, of course, Anthony Hewish made all of the antennas, etc., but the actual discovery and characterization was by Jocelyn Bell. She did not get it, and sometimes people call her Jocelyn No Bell, because she did not get a Nobel Prize. But fortunately, she actually did get many, many other awards, and certainly the credit for this discovery she certainly received. So anyway, in this case, we have the supervisor and the student. Supervisor got the Nobel Prize, the student did not. Anyway, we will go back to that. And actually, a few years later, Huss and Taylor discovered a neutron star binary, a pulsar with a companion, and they actually show how the orbits of this pulsar, right, gets closer and closer in. Basically, it's in spiral, and the in-spiral rate was consistent with the predictions from gravitational waves or from general relativity. So this was the first, in a sense, indirect discovery of gravitational waves from the in-spiral of this neutron star binary. And for that, they actually got the Nobel Prize in 1993. The story goes that actually Taylor, well, that's just a story, of course, they got the call in the middle of the night, you got the Nobel Prize, and Taylor, being a decent person and also knowing the story of Jocelyn Bell, asked, okay, and what about my student Huss? Did he get the Nobel? They said, well, no. So he said, okay, I don't accept it unless you give it to him too. So Huss got a call in the middle of the night. He got the Nobel Prize. He doesn't understand, goes to the basement, finds his PhD thesis, which he forgot a long time ago because he worked on plasma since then and not all these issues, and understand why he got the Nobel Prize for. Well, this is just a story how it goes, but both of them got a Nobel Prize, both the students and the supervisor in this case. Okay, but let's go back to supernovae. So since then, people started to look more and more supernovae, and they started to have sub-classification, and they realized it's even more complicated than what they thought in the beginning. It turns out that type 1 supernovae can actually be divided into two. Those will have strong silicon lines, and those that have weak or don't have any strong silicon lines. And they basically see in this case, they also divided the case where you do see helium or you don't see helium in the spectra. So this was type 1a supernova, type 1b, type 1c, and you still have the type 2, which shown hydrogen. Okay. Later on, what we realized that all of these things, as it turns out, are related to some kind of a core collapse supernova. The basic model, though not very well detailed, of a massive star that collapses, while the other part is actually coming from a different direction. So people at this point realized that most of the elements in the universe are not coming just from the Big Bang, but also from stars, right? What happens inside the stars and what ejects much of this material is through supernova, and many of the production, some of the heavier elements actually happen in supernovae. And there's a very famous Burbage Square, Fowler and Hoyle review paper that really kind of gave this picture of the element formation in the universe. And for that and for other understanding of stellar evolution, both Chandrasekhar and Fowler got the Nobel Prize in 1983. In any case, this was another, in a sense, paradigm loss, because in the past, people thought that no, everything was just formed early on in the universe and nothing changed since in terms of the elements. And the realization that things actually happen in stars, that new elements are actually formed all the time, is something that today we consider as kind of as trivial, but this was not trivial in the early 20th century, even almost up to the mid of the 20th century. And this is an important contribution in that context. So we are stardust, indeed, at the literal level. Most of our components are coming from that. So Fowler and Hoyle in the 1960s actually suggested the first models or detailed models for supernovae, both the core collapse supernova, but also a different kind, a thermonuclear supernova. What do I mean by that? So if you think about that, when we look about the mass number of the elements, right, and you can see about the binding energy, when we fuse atoms, as you very well know, you can actually gain energy. Okay, it's kind of an exothermic, but once you get to a stable ion, above that, it's actually an endothermic. If you want actually to get higher elements, you actually need to put much more energy. In a sense, core collapse and thermonuclear supernovae are actually working on two sides of this thing. If you think about it, core collapse supernova, when they actually collapse, they need to put some of the energy, as they go of the gravitational energy, into somewhere. For example, they can photodissociate ion, okay, as one way of doing that. Or at some point, electron can actually go into the inside the proton become neutrons. For what happens in stars is we actually gain energy by fusing the elements. In a thermonuclear supernovae, as I'm going to tell you a bit, white dwarfs, for example, you have very fast runaway case where things are fused at very high rate, much energy is ejected, the temperatures rise again, and even faster nuclear processes happen until you actually burn all of your material into these very high elements, a lot of them into basically iron or things that later on decay into iron. So people started to have a basic understanding of the ideas, at least for forming both core collapse supernova and thermonuclear supernova. At the same time, on the observational side, things became even more complicated. At least in the core collapse regime, you can actually even type 2s that were simpler before that. People realize that if you look on, they have different kind of light curves and behave a bit differently, and they start having a more complex, basically a supernova zoo, in a sense, of different types of supernova, but still, all of this regime was understood as basically various types of core collapse supernova, which to this day are not completely well understood, and certainly the models are still lacking. There are better people than me can actually tell you about that here in Monash. But I'm going to focus on the other side, which is thermonuclear supernova and type 1a supernova. So what are the basic models for type 1a supernova that we have today? The basic idea is they have a carbon-oxygen white dwarf, usually coming from a 6 to 8 solar mass, up to 6 solar mass stars from these and the end of their life. They are held by the generate pressure, as you know, and once we put more material on that, and either through merger or through accretion of material, you can accumulate mass, leading to very high temperatures and density and pressures of this white dwarf. And because it's degenerate, it doesn't have this feedback like in stars that they can actually expand and cool or something like that. It's degenerate, so the temperatures rise, and you start having extreme nuclear burning. And that was the basic idea of Hoyle and Fowler, that once you get to this point, we have this runaway process of thermonuclear processing, and you explode the star. So if you have a white dwarf and you start this detonation, in a sense, you start something which looks more or less like basically an atomic bomb. The main reason it is because it is an atomic bomb. Okay? But actually it's more like a hydrogen bomb because it's a fusion bomb. But you actually have exploded all the white dwarf. During the explosion, as I said, you burn all materials into very high elements like iron, but you also see a lot of intermediate elements like silicon, magnesium, basically most of the intermediate elements that you know are also coming from this supernova. How do you know? We can actually see them in the spectra. And, well, we see all the material around us, of course. But we think there are actually these materials coming from this kind of explosions. So these are, as you know, not only used for not only as to the explosion, but their light curve, okay, behaves in a very interesting way. So you have the rise and fall. And what happens is it produces a lot of radioactive elements like nickel-56, and this actually drives the light curve evolution. It first forms in the first few seconds of the explosion, and then over time the whole material of the explosion expands. The nickel-56 decays, or actually it's cobalt-56 and nickel-56, they decay, they produce positrons which annihilate, produces photons, and you see all of these photons coming through. So later time, when you're not enshrouded in this cloud of material, you start seeing even directly almost kind of the exponential decay of the radioactive decay of this cobalt-56, which drives a typical timescale of about 70 days for coming from the decay, from the half-life, in a sense, of these elements. Okay? As you know, these, as it turns out, these can be actually standardized and produce very nice standard candles that were used in order to study the cosmological evolution and the way that our universe expands. So it's, even though at this point people did not really understand the full mechanism of the explosion, they already can be used, even in phenomenological level, to really measure distances in the universe. And this, of course, gave rise to the Nobel Prize in 2012 for the accelerated expansion of the universe. By the way, in this case, right, as you might know, there were two main groups led by Perlmutter on the west coast of the US, and the east coast in Harvard. It was basically Kirchner who was supervising the postdocs, Schmidt and the PhD student Rees. Those two actually, really pushed forward for this project. But in the end, in the Hubble, only 3 people can receive it, so they had to decide. So Perlmutter got it for his group. But then Rees and Schmidt got it, and Kirchner did not get it. So now the students got it, or students postdoc, and the supervisor actually did not get it in this case. So it's interesting evolution, social evolution of the Nobel Prizes in that context. So what is the origin of type 1a supernova? So I gave you a very long introduction to kind of bring you a bit with the history. As I said, I like to tell stories. And we are very important. They produce most of the iron elements in the universe, a large fraction of the intermediate elements. They serve a standard candle, I just told you. They actually have important role also in feedback mechanisms for galaxy formation. So we had this supernova zoo, but as it turns out, even type 1a supernova, we realized over the last 20 years, are not very simple. Turns out there are many peculiar subtypes of type 1a supernovae. Some of them might not even be type 1, but type 1a, but even type B, 1b, which are related to them. So people started to see in these large surveys that you can actually subdivide type 1a supernova to various subtypes with very different types of characteristics. So if we want to understand the origin of supernuclear supernova, type 1a supernova, we need to be able to understand not only the standard, normal, regular type 1a supernova people like in the context of the standard candles cosmology, but also all the subtypes, because they might all be related, and any successful model should be able to explain all of them. And these subtypes are actually not very rare. If you actually look on all of these subtypes, each one of them can produce significant fraction of the overall type 1a supernova rate. And so people once thought about them as being exotic, but as it turns out, about maybe even more than 50% of all type 1a supernova are actually not the standard type 1a supernova that you usually hear about, but all of these various types of other peculiar supernovae. So what could be the origin of them? Well, we can have some clues. For example, we see that these different subtypes also have different host types galaxy distribution. So if we look on different types of galaxies, we see that normal type 1a supernovae, they are usually, the majority of them are actually produced in so-called spiral galaxies or star-forming galaxies. At least 50, 70% are forming these galaxies, while some of the subtypes behave differently. Some of them are actually much dominated by very early type galaxies, so very so-called long delay time distribution. You formed stars, but only very, very later after you actually have producing the supernovae. And so basically it suggests you have different kind of progenitors for this. Otherwise, how can they actually behave so differently? The other clues we can actually get from the kind of the HR diagram, in a sense, for supernovae, we look on the absolute magnitude of supernovae, okay, the peak luminosity in B in this case, and you can look on how long does it take them to kind of fall down. How rapid do they go from being very bright into being much fainter. So you can take like this 15 days after peak and see what's the magnitude that you can see. The difference between them is called so-called the delta M15, in this case in the B band. So at least to first order, it gives you kind of a division of supernovae in the phase space of basically the luminosity and width of the light curve, if you can say it. So what we see here is kind of the so-called Phillips relation, what's really amounts to the basic stuff that people do in order to get the cosmological, the standard candles. You can see that all the supernovae are kind of fall on some kind of phenomenological fit. So in a sense, once you see a supernova of some, even if you don't know the brightness, but you see how long it takes it to fall down, you can go here and say, okay, this is the brightness, and then effectively, because you know the brightness, you can actually check the distance, compare the absolute magnitude compared to our observed magnitude today. So this is a Phillips relation, but you can see that normal type 1a supernova sits around here, but then you have all of these subtypes which actually sit in very different parts of the phase space. So what are the main predictors? Well, two main, let's say, directions were suggested. Either you have a single white dwarf with a companion, a binary, a white dwarf with a white dwarf which actually accretes material from companion. So it starts from some lower mass CO white dwarf, which then slowly accretes material, hydrogen and helium, burn them into carbon and oxygen, and slowly grows in mass up to close to the Chandrasekhar mass of about in this case, typically at about 1.38 solar mass or so. And when they get to become extremely dense and with high temperature in their core, at some point some fluctuation is enough to ignite them, and then they explode through thermonuclear explosion. So this is so-called the single degenerate model, because you have a single degenerate white dwarf with some companion. It could be a main sequence star, it could be a red giant, or an asymptotic giant branch star. In the other model, you have the double degenerate, two white dwarfs that form in a binary, and as they come close to each other, very likely after common envelope evolution, that people here in the audience study, actually inspire through gravitational wave until they merge, and then they actually ignite and explode. Okay, nice. However, the problem is that actually no successful model for the origin of type 1a supernova has actually been really produced. Many groups have done this explosion of different, both a single degenerate, double degenerate, and some of them actually successfully produce things that look like type 1a supernova in the models. However, none of them will actually be able to really reproduce both the specific properties of a given supernova. You might know, so one model which is fine, but then you look on other cases or other combinations of masses, for example, and you don't get actually the variety that we see for type 1a supernova. And more than that, you actually cannot expand the rates of type 1a supernova, the delay time distribution, the overall host galaxy distribution. All of these things together, no one model could actually really reproduce very well, both in the double degenerate and the single degenerate models. As I said, any good model should be able to express both the composition and structure of the explosion, the spectra, the light curve, the rate of energetics, the rates, the data distribution, so you have physical properties and population properties, let's say, or demographics. So the diversity, subtypes, all of these things. And the question then, okay, I actually won't talk about any specific models here. I'll try to actually focus on the next thing. If you want, you can ask me more about other models, why I think they have problems. But let me focus on what I think could be the solution. So the interesting thing that we suggest is, first of all, that in some sense, everyone was right. Okay, how can that be? Well, every kind of the model, or almost any type of the model that people suggested, we think they actually have some, in a sense, can explain a bit of some of the subtypes of supernovae, which is nice. Still, the major part, I think, could be explained by a basic model, which I'm going to introduce now. And in my model, we're actually focusing on the double degenerate. So our models also discuss a double degenerate, and as I said, I actually won't discuss other models. But you can think about different types of white dwarfs. We have carbon-oxygen white dwarf coming from up to 6 solar mass stars, which enter the evolution and form a white dwarf. You can have oxygen neon white dwarfs, which typically come from about 6 to 8 solar mass stars. And you can also have these helium white dwarfs, which in principle, you could get from very low mass stars if they ended the evolution, but their lifetime is much longer than the Hubble time, so they shouldn't exist in principle. However, we do see helium white dwarfs, okay? And this range, by the way, this is more or less the range of masses that we expect from them for CO white dwarfs, helium, and oxygen neon white dwarf. So how do you actually get helium white dwarfs? Well, if you have a binary, okay, and one of the stars evolves, burns the hydrogen in the core into helium, you have a helium core, and now if you have a companion that strips the envelope of this red giant, you can actually left with this helium core, which then cools down and eventually become a helium white dwarf. So in a sense, you start with a more massive massive star that can evolve in Hubble time, make it a red giant, strip it, and then you are left with this helium core that can produce a helium white dwarf. Of course, if you do it much later on, you start burning the helium in carbon-oxygen, you have a carbon-oxygen core. If you stripped it in this case, you just have a carbon-oxygen white dwarf. But however, of course, you have the intermediate regime. So let's say you strip a star which has a bit more massive helium core already, and you strip it, you have this helium core, but now this helium core is massive enough and hot enough to start helium burning. So it starts helium burning, you start having a carbon-oxygen core. However, it's actually not massive enough to burn all of the helium all the way to carbon-oxygen. So what you are left with is a strange, peculiar hybrid helium-CO white dwarf. So you have a massive CO core, but a helium fraction which is quite significant, from 5 to about 20%, depending on the mass of the white dwarf. So this was already suggested in the 80s, but did not really receive much attention. And our focus was actually trying to say, okay, are these hybrid white dwarfs important? And what I suggest, they're not only important, they're actually critical for understanding of type 1a supernova, and they play the key role in the type 1a supernova progenitors. You could actually study the evolution of this hybrid white dwarf. We did it in various, both using MESA models and other models, both in binary and single configuration. In a sense, we get very nicely consistent models for how these hybrid white dwarfs look like. Basically, not surprisingly, you can kind of find between CO white dwarfs and helium white dwarfs in terms of the kind of mass radius relation, temperature, because they are kind of in between in many ways. They are not actually easy to identify, first of all, because they can only be found in very compact binaries, which actually went through stripping. The other thing is, in order to actually differentiate in between other white dwarfs, you need to know exactly the radius, temperature. It's pretty difficult. You can only do it in eclipsing the white dwarf binaries. And even in that case, it's pretty difficult to really identify the real radius, because it's sometimes dominated by even a small amount of a hydrogen or a helium shell that determines the size. So actually identifying directly is difficult. Also in Caltech, actually on a survey of about 7 white dwarf eclipsing binaries, they found one of them to be potentially consistent with being a hybrid. So hybrid white dwarfs reside in this regime of phase space. So this is the size and the mass. And mass, as you can see, that's kind of between about 0.4 to about 0.75 of solar mass or so. And that kind of, you can see in terms of masses, they overlap with both CO white dwarfs and a bit with helium white dwarfs. So why do you think they are so important? Well, first of all, they're just a new component. So we considered all the other cases of combination, and none of them actually produce a normal type 1a supernova. Well, this is not exactly true. Massive CO plus CO white dwarfs, when they merge very massive, about solar mass, did produce something which looked like a type 1a supernova, relatively bright and slow evolving, but overall normal. They cannot produce other ranges of the phase space supernova, but it's not really like none of these can produce. Some of them can produce something. This thing is just a completely new element, so you can just ask, okay, when it merges, does it do anything interesting? And the answer is generally yes. But before that, we need to think, okay, even if they do anything important, why do we care? If they're very exotic, they are very rare, we would never be able to reproduce the overall rate of type 1a supernova to begin with. So a very simple question you can ask there is, for example, population synthesis, with all of the caveats that you have with population synthesis models. Turns out that it's quite robust across different models with different assumptions, that about 25% of all white dwarf mergers involve at least one hybrid white dwarf. So hybrid white dwarfs could be rare overall about the white dwarf population, but they're highly frequent in the cases of very compact white dwarf binaries that merge. So we have about 25% of all mergers involving a hybrid. Is that enough? Well, observations tell us that we need only 15% of all white dwarf mergers to end with a supernova in order to explain the whole rate of a type 1a supernova. So not only we have enough, we actually have more than enough that even if a fraction of them do not explode, it's enough to explain at least the rate of type 1a supernova. But that's only if they actually produce type 1a supernova, which I have not shown you yet. So what I've seen here, by the way, this is just the population synthesis results. You have one white dwarf mass, the other white dwarf mass, and you can see how kind of the mapping of where do they stand in this whole regime. And this division, I'll tell you a bit about later on, but you can imagine it's related to different types of type 1a supernova. Okay? Hybrid white dwarfs, and you can see are these secondaries in this case of about 0.4 to 0.75 something solar mass, which participate in many of these mergers. So in order to really model type 1a supernova, what do we need? Well, first of all, we need to be motivated about what are the progenitors, which I motivated you that hybrids potentially could be interesting. We need to model how they look like, both the CO white dwarf and the hybrid white dwarf, which can do using, for example, MESA model. These are 1D models. We can put them now in a hydro simulation. We have two white dwarfs, and we actually put them in the hydro simulation and see how they merge. Of course, in mergers are 3D processes, so in principle, you need to do it in 3D. The problem is that 3D models, like here that we did, are a bit complex and highly expensive if you don't want to also include all the thermonuclear processes that are involved in that. So what we did as a first step, but now we're already starting the second step of doing 3D, is doing it as 2D models. How can you do mergers of white dwarfs in 2D? Well, the idea is the following. What happens when two white dwarfs come together? The less dense one actually disrupts by the more massive one. It disrupts and basically forms a disk around the more massive white dwarf. So now we have a white dwarf core and are surrounded by a disk. This disk is quite symmetric. So in a sense, we go to a very actual symmetry configuration. So in a sense, we can now model it in 2D. So this is what we do. So we started from the second stage. We say, OK, we have a white dwarf. And now we look on the disk around it. This is kind of a cutoff. Okay, so this is not the second white dwarf in a sense. It's the debris of the second white dwarf after it's disrupted. So in our case, we have a CO white dwarf. It's pretty compact. And a debris disk of material coming from, for example, in this case, hybrid white dwarf. And you can follow its evolution and see what happens to the disk and what kind of, and we do it through a full thermonuclear evolution. Once we do that, the thermonuclear evolution, even though it's, you can do it in 2D, even then it's quite expensive, especially if you need to include all the network of nuclear processes. So we usually use smaller networks where most of the energetic stuff happens in just small networks. But if we really want to look on the detailed composition of the results from this supernova, we do a post-processing analysis, and we can actually get the whole evolution of this network of nuclear processes and get the elements from the supernova. Once you have all the elements, you have the velocities, temperature, etc., you can then do a radiative transfer model, follow light as it goes through the explosion, and see how it should actually look like to observers. For me, the series took like at least almost 3 years to really develop all these things, from zero through the population synthesis, stellar evolution, SPH hydrodynamical simulation, AMR models with thermonuclear evolution, post-processing, and then radiative transfer to really get to the position where I can say, OK, let's compare with real observation. So I still remember the first time I looked on our models, the results, and compare it to a type 1a supernova light wave spectra, and wow, it was amazing. For me, I didn't have many cases of the series that I could look really directly at a detailed level. So maybe it's not that surprising. Each time you can actually explore white dwarf, it produces somewhat related and similar. But it wasn't clear to begin with that these white dwarf kind of things would actually explode at all. And they do. Okay? So once you can do that, you can actually compare directly with observation and say, OK, are we OK or not in terms of producing the observables? More than that, together with population synthesis, if we have a grid of models of different combinations of acids, we can say which types of models produce supernova, which are not. And we can even look on the population synthesis and say what kind of host galaxies should they have, the rate distribution, overall rates. So do they explode? Yes, they do. Okay. So what happens is that you have this debris disk. Now on a viscous timescale, they start to evolve inwards. Okay? They start accrete onto the CO white dwarf. Now, you need to remember these hybrids have a lot of CO, but also a lot of helium, which is very different from regular CO white dwarfs. Helium is much easier to detonate. Okay? It can be detonated at much lower temperatures and much lower densities. Okay? So in a sense, it can catalyze explosion, which otherwise would require very, very high temperatures. You all know that, right? We started with burning hydrogen and helium, and only at higher temperature can we burn, for example, carbon dioxide. Here we talk about not just a slow burning, but about really a detonation process. But in principle, the ideas are similar. So what we found is that just, I don't know, after about a few tens of seconds, when the activities have this helium detonation at this point, okay, this helium detonation starts to go through the white dwarf. One of the important things that it does, it actually compresses the inner part of the white dwarf, the CO white dwarf, up to the level that even the CO now can detonate with a CO detonation. And we get a second detonation, which is close to the center of the white dwarf. And that actually burns everything and explodes the whole white dwarf, throwing everything and burning everything. If you look on the, for example, nickel-56 production, okay, the main product that really drives the light curve, you have the first helium detonation, produce a bit of nickel-56, but then most of the nickel-56 actually produce in a second detonation. This is a cumulative plot of the same. You see a small production about, it's not that small actually, 0.05 solar mass of nickel, it's not that small. It's already, even by itself, it would produce something which looks like a very faint supernova. But then, with the production of this nickel-66 and the CO detonation, you get something which is comparable to what we know is inferred for type 1a supernova, about 0.6 solar mass of nickel-56. Nice. So we actually have now a model which seems to actually produce something with the right elements. People always ask, or people ask me sometimes, how can it produce so much nickel? What is the problem? Previous models, where people use more massive CO white dwarf, they couldn't actually explode low mass white dwarf, only the more massive ones. One of the reasons, and even if they exploded, they didn't produce necessarily enough nickel. The issue is that for low mass white dwarfs, if you just look on densities above 10 to the 7, okay, grams per centimeter cubed, low mass white dwarfs actually don't have these densities. Why is that important? Because in order to produce nickel, you need to burn things at very, very high densities. And these would not do that, and this is why you usually don't get these high nickel abundances, you don't get type 1a supernova light curve scatter. However, because we have this double detonation, people discussed double detonation in the past, but not with these energetics. We have a lot more helium than people discussed in the past. The compression is much, much stronger, and you can actually compress the core, and now all of this core after the helium detonation, this is after the helium detonation, compresses, and now when the CO detonation occurs, it occurs at very high density, and you can produce these high amounts of nickel-56. Okay, good, we get the elements right, overall we get the explosion. Does it look like a type 1a supernova? So we can compare with volumetric light curve. We don't have many of those type 1a supernova. We need to follow volumetric, we need to follow all the various different bands, but we have for some, and they're actually quite comparable. Not all of them. We cannot, for example, produce very higher luminosity type 1a supernova, but they can actually produce a typical normal type 1a supernova light curves, both in the volumetric. I'm talking about the volumetric because there are many assumptions go into radiative transfer. The volumetric light curve is less affected by these assumptions, let's say. But actually, if you do look on the different bands, BVRI, for example, they actually do a pretty good job. Less so with the B in some part of it, but it's actually not as surprising. The assumptions are made for radiative transfer. It happens in local thermonuclear equilibrium condition, and after about 20 days or so, these conditions are not as, these assumptions are not necessarily the best. We have, there are other radiative transfer codes that can do that, but very few of them. We don't have them right now, but in principle actually do a pretty good job. If you look on the spectra, compare with observations, okay, this is the best observed supernova, 2011 FE, and this is one of our models, you actually get a pretty good result. If you actually compare it to other models of theoretical models, usually they produce something very similar, so this is successful. Okay, nice, so we get the physical properties of single supernova more or less pretty nicely. Are the rates fine? Well, I told you we have 25% of white dwarf mergers include a hybrid. Well, some of them include a hybrid and a helium white dwarf. Those cases, for example, do not produce a type 1, do not even explode. So not all of them produce it, but as it turns out, if you actually look at the daytime distribution, how long since star formation did the explosion occur, these are kind of models inferred from observation, and these are various different models that we have, depending a bit on metallicity, etc. They actually do a pretty good job. First of all, I think they're one of the first models to ever really explain the total rates. But more than that, they actually produce it, both the total rates and the daytime distribution. Even these parts, which maybe depend on metallicity, it seems like a big difference. This is actually a factor of 2 at most, and really depends on assumption. So even this part is pretty nice. Okay, good. So we have a model which potentially produces normal type 1a supernova, produces the rates correctly, and the daytime distribution correctly. And I'll get to the caveats in a second too. Interestingly, they potentially can produce not just a normal type 1a, but other type of supernova. So if you go to our HR diagrams, okay, and we put some of our models there, okay, this is just a zoom in, okay. Not many people actually did double white dwarf mergers in the past. So these correspond to all of the models that have been done. Maybe I missed one of them. Each one of them is not for a range of models. This is actually one model, one explosion case. And this is just the range of the from, if you look at it from different observing angles. So as you can see, past models could produce normal Titan 1a supernova mostly in this regime. And there were some peculiar ones that suggested could be happening in this regime. Our models actually complement these, okay? And they are produced in this range. And actually, the relative transfer, is not trustworthy to very high rates. So more or less, I would say this is more or less the range you can actually go through. So they cannot. What we cannot explain is these high luminosity ones. Okay. Here it seems like most of them are high luminosity ones, but this is related to Malmquist bias. Actually, there are many of the supernova, at least about 50 to 60% are actually in this regime where we stand. Okay? On the other hand, we certainly cannot explain these more luminescent, slower ones. This could be related to relative transfer model. It's certainly possible. Talk with several of the experts on relative transfer. They say this might not be that of issue, but if it is, I would say that it's actually fine by me. I was first he said, why I cannot reproduce even those? Then double white dwarfs, CO white dwarfs, 1+1 solar mass white dwarf, actually do produce them. I'm fine with other models actually producing some of the first place. These methods should also happen. They should produce something. It's actually very nicely that they kind of complement what we cannot reproduce is exactly what they can reproduce. What they cannot reproduce is actually the other stuff that we can. So that is so in principle it's very nice. We actually can explain it's this regime of the phase space. And as I said, the distance distribution, etc., are fine. Even actually, we don't have to, but in principle, we actually include the more massive white dwarf that other people do. They add a bit, but the majority is actually about 50 to 2/3 of them are actually coming from the hybrid white dwarf merger with the CO white dwarf merger. Nice. What about? So I told you about normal type 1a supernova, but what about all the rest? Well, interestingly, a few years ago, I led the characterization of a new type of supernova, very strange one. It's supernova that was observed in an early type galaxy, it's an S0 galaxy, no star formation. And more than that, it's actually very far in the halo of this galaxy. By the way, how much time do I have?
5 minutes.
5 minutes, okay. Good. So, and it turns out it was a type 1b supernova, which I just told you is a core, we thought at the time was a core collapse supernova. But core collapse supernova should come from massive stars. There's no star formation, certainly not in the halo. So what the heck, what's going on? No, we look whether we might just miss some star formation around. There's no evidence, even in deep UV, infrared, etc. Nothing there. So what was it? Well, turns out also the spectra was very, very strange. It was a type 1 supernova, but it was extremely calcium rich. At late time, people see that there was very strong calcium lines, and the relative ratio between the calcium lines and other lines was extremely high compared to any kind of other supernovae, and it was a bit, quite a bit strange. More than that, they actually produced very low mass. If you actually inferred from the spectra how much mass was there, it turns out it was very small, like 0.3, 0.4 solar mass. That's completely inconsistent with core collapse supernova from a massive star of at least 2 solar mass cores, etc. So as it turns out, we realized that this could actually come from some kind of explosion which involved a lot of helium, but a thermonuclear explosion. So a CO white dwarf accreting something with a lot of helium, exploding, and you can see all of this helium. Well, in type 1a supernova, you don't see it. So I told you about the hybrid models that we have a lot of helium and it explodes. Well, in our models, in the end, all of the helium was burned. We didn't get actually any helium left around, which is good because type 1a supernova don't show it. But these ones do show that. So if you actually go back to our models, you can see that I told you about those ones, but we also got some extremely faint ones. Actually, some of them falls exactly in the space where we expect these so-called calcium-rich transients to occur. So what's different about these models? Well, what was different is everything that I told you about happening. You have this accretion, viscous accretion onto white dwarf. You have a helium detonation that compresses the white dwarf. But if the white dwarf, CO white dwarf is actually low mass, not very high mass, even the compression is not enough to really detonate this low mass CO white dwarf. So what you get is the helium detonation, but you don't get the CO detonation. So the helium detonation gives us like maybe a few 0.01 solar mass of nickel. It's very faint. It's not very efficient. It not explodes whole white dwarf. It did not burn off the material. So you are left with a lot of helium around. So now you have a very faint explosion with a lot of helium. It's more than that. When you burn nucleosynthesis burning, right, you start from these lower elements. You start burning all the way to iron if you are very efficient. But if at some point you become less efficient, so the density goes down, you're kind of stuck in the middle before you get all the way to nickel-56 and iron. So what you get is a tail of iron elements, a lot of intermediate elements, and a bit even below that. What are the intermediate elements? Well, actually dominated by calcium. You have to produce tons of calcium, very faint supernova, helium-rich. Actually completely consistent potentially with a calcium supernova. So this also explains why calcium supernova kind of, they don't have a continuum of supernova from these ones to these ones really. And the thing is that it's a bimodal. Either you have a second detonation or you don't have, depending on the mass of this CO white dwarf. In effect, it's actually not just that. You can actually even switch the cases. You have a massive hybrid white dwarf that actually disrupts the CO white dwarf. Then you have a CO core, a helium shell, and sandwich with the CO white dwarf debris that accretes on that. It produces very similar faint type of supernova that actually might also explain not just this, but also other kind of supernova, which I don't have the time now to talk about. There are other peculiar type of supernovae, okay, especially the so-called type of SNE 1AX or 2002 CX. I won't talk about them. I just tell you that we have they're actually coming from completely different metal, singular degenerate. So these parts, I don't think are actually coming from our hybrids. If you want, you can ask me about those, but I don't have the time. So I'll try to close down. Basically, the calcium rich can also be explained very nicely and other supernovae. So in a sense, you can actually now look on the population, and now we actually have a global picture of type 1a supernovae and what actually makes the subtypes and division. And that's actually related to different types of CO white dwarfs and hybrid white dwarfs and the relative masses. So if you have total mass of above about 1.3 solar mass of CO plus a hybrid white dwarf, you get normal type 1a supernova. It's coming from this regime. If you get very low mass CO or hybrid white dwarf that disrupt another low mass white dwarf, so total mass which is low, you get these two types of peculiar type 1a supernovae. Very massive ones, okay, or very luminous ones could actually produce without a hybrid white dwarf, and these are maybe the previous model that people suggested, maybe coming here. And you have also the intermediate regime, which is related to some of these other ones that I didn't have time to talk about, but I can talk more. So now we have a global understanding of what's going on, what divides one case from another, and what are the physical processes relating to it. So some of the aspects could be a continuum between various types of more explosive and less explosive, but at some point there's a bimodality when you don't either have or do not have the second detonation, which explains the extremely faint supernovae, some nuclear supernovae. So this is more or less kind of the phase space of supernova that we think coming from the different kind of explosions. Do I have one more minute, last minute? Okay. So I told you that everything was about 2D, right? But we're going on 3D, and these are very important. So now we're actually starting with 3D. And this is where we're going to leave you with a bit of a cliffhanger. So we started with 3D. It's actually a collaboration with Heidegger Packmore, German group, and do these 3D simulations. So again, we took a relatively CO white dwarf of 0.8 solar mass, a hybrid which is actually pretty massive compared to most of our models. So, and I'll talk about it in a second. What you see here is the following. So, okay, so you can see the density, but then you have the temperature, you have velocities, you have here you have the helium, and then you have carbon, and then you have nickel. Of course, in the beginning you don't have any nickel, no nucleosynthesis, and they start kind of coming together, and the hybrid white dwarf start to mass transfer of the helium shell that it has onto the CO white dwarf. At some point, before the hybrid white dwarf is disrupted, so that's not like what we have in our models, okay? You start having a bit of a helium detonation on the CO white dwarf. You see that the explosion here, the temperature is very high, and you start, it's very difficult, you don't actually still produce really nickel, but you can see but you can see kind of the evolution. It starts to go, this detonation shock goes all the way around the white dwarf, okay? And people actually suggested this kind of mechanism happened even before we did. But you also see this strange tail coming here, which actually, if you look back here, this actually goes back to the hybrid white dwarf. So what's going on here? Well, it turns out that you start having this shell of helium. It starts to detonate, explodes, kind of explosion, the shocks go around the white dwarf, but at the same time, it also goes back to the hybrid white dwarf. So what awaits the hybrid white dwarfs? Tons of helium, right? So turns out it goes all the way back, and now the helium on the hybrid white dwarf, original one, again, before it's disrupted, start to detonate. On the other hand, the CO white dwarf, they don't detonate at all. We have only the helium detonation, but not the CO detonation. Okay, you continue. You actually compress, like I suggested, it could actually happen to the CO white dwarf. You actually compress the hybrid white dwarf, and you get a CO detonation in the core, and the hybrid white dwarf explodes completely, leaving behind the CO white dwarf. So that's completely different to what I told you, right? there was no disruption of the hybrid white dwarf. You do not actually get to the position where you have a disk. You actually get a detonation before that, which does not explode the CO white dwarf, but does expose the hybrid. So that does not produce a normal dichromatic supernova. So this is one of the simulations. However, if you go to lower mass hybrid white dwarfs, they do not explode. They do not do this. Okay? So even if they have some burning, they're actually left behind. They are going to be disrupted, and we actually see this in our newest 3D simulation from just weeks ago. So they're actually ready for being disrupted and form a disk. So we're still there. This is the point where we are. We're seeing the 3D should work, actually work, maybe not for the whole of the phase space that we thought about. And this is basically our models for type 1a supernova. So thank you very much.
Questions?
How much more expensive was it to run that than your 2D model?
So our 2D models usually run on a few hundreds of CPUs, and it takes like a few weeks for one model. Maybe 2 or 3 weeks maybe. This one 3D model took us, I think, at the level of tens of thousands or even a bit more than that CPUs, and that took about 2 months, I think. So
no, so the keys to lots more 3D.
Yes, it's, as you know, 3D, much more complex, so indeed, it's much more difficult. This is a repo models. Our model were done in Flash, the 2D models, this is a repo models, okay? With the special editions of the nuclear synthesis, stuff like that, that Heidegger Packman is added to that.
Do any of the students have a question? Yes, please, Alex.
Just a question on that 25% number you sort of grabbed. So is that just a pops-in result using that 0.4 to 0.75 mass bracket, or?
Okay, so in our pops-in, so we did a detailed model, Mesa evolution, of what produces a hybrid. Okay, when we took these conditions, put them back as conditions, the filtering for population synthesis, and say, okay, these ones under this condition should produce a hybrid white dwarf, and this is how I identified the hybrid white dwarf in this case. So it's not just we took the range of masses. It's not. It only happened in binary evolution, obviously, and only under specific conditions where the splitting happens in some cases. So this is coming from it's based on the full cell evolution, but it's a population synthesis, of course. It's just put in some kind of a specific filtering, of course. Okay.
You looked at one type of hybrid, but do you have plans to look at other kinds like oxygen, neon, magnesium, carbon, mixing the things around?
So actually, we do our various combinations. We look on CO white dwarfs, and we actually got the same results as other people did. That with 0.6, 0.7 solar mass, or even 0.8 solar mass CO white dwarfs, we don't get an explosion. So CO did not work for the low mass ones. High mass ones, especially if they're comparable, the assumption of a disk is not correct anymore, because if they are really of comparable mass, and not really one of them disrupts before the other, they actually kind of merge in a much more complex way. We cannot run cases where the mass ratio is too similar, or there are two masses too similar. But in any case, we did run CO and got similar results to other people, no explosion. We have CO and helium white dwarfs, no explosion. In this case, these were lower mass helium white dwarfs. In this case, they are much more puffy, and when they disrupt, their disk is much bigger, and the densities are much lower, so you never get to a helium detonation. What you get is just a puffy envelope around the CO white dwarf. So CO and helium or low mass helium white dwarfs did not work. What worked for us was that oxygen, magnesium, neon white dwarfs with CO white dwarfs is something we are doing now. They do not explode, which is not necessarily surprising. If in neon, you need to be even higher temperature to ignite. So what usually happens, you might actually ignite some of the disk around it a bit, but it's very difficult. And what we think could happen is you have an accretion-induced collapse where the whole oxygen neon white dwarfs, if it accretes enough mass, collapses into a neutron stars. This is not something we model. But the early evolution, this one did not explode, but it did produce some very ultra-faint supernovae, just from the material in the disk, that some of it burned a bit. So they did not contribute to any of these. And actually, we have some predictions for supernovae that will be observed in the future, hopefully with LSST, which are even fainter. So in that sense, actually very nice that we have predictions. But this is kind of more as the phase space. So we did look actually on the phase space a bit of that, not as much as we looked for the hybrid, where we actually really did a grid of different hybrid white dwarf masses, different CO white dwarf masses, to see where the transition from explosion to not explosion occur, etc., and what range of luminosities, for example, we can get from all of these things.
For the people in the audience who are earlier in their careers, I should have mentioned that Hagai just won a €2 million grant from the European Research Council, which means that he will, over the next few years, be hiring lots of people to do this kind of exciting work. So if you're interested, come chat with Hagai. But I suggest we chat with the guy over lunch and take a break now. So thank you very much again, guys.
Thank you.